Very nice to meet you all virtually. And I'm just going to start where Greg finished. So he showed you how these type of models, where we have an equivalent circuit network and the thermal model, and we couple together, and we are mostly focused on modeling the behavior of the active material, so the things that make the battery a battery, that deliver energy. But there is a lot of focus, especially in our group, but not only, also to model the non-active components. So he showed you here how modeling the can of the cylindrical cell actually very much changes the behavior you get in the model of the system. And of course, this is the performance that you want to be evaluating if you are, for example, a battery engineer, want to choose your cell or want to design your battery or want to choose a thermal management system. He also mentioned this Tesla tabless cell, so the fact that the model you create with these non-active materials as well as the active materials can show us that you get this inhomogeneity in density across the current collector, which we know, hopefully you can see my mouse. Let's just put it like this. Yeah, so now it's a red dot. So the current inhomogeneity close to the tabs leads to a temperature increase because you have a higher current density. And this temperature increase will lead to an unexpectedly early degradation. And so you want to avoid this. And here you see what Tesla designed as a cell. So inside the can, they now have basically a continuous tab to draw current from everywhere to avoid these waves that you see here in the current density and thus in the temperature then that the current collector sees and thus in the degradation. So this is inside the cell, and before Tesla, the general opinion was that first, this would be quite difficult to manufacture, and secondly, this would add a lot of volume and mass to the cell. So when you buy a battery, you don't care so much what its energy is. What you care about is energy density. So how much energy it can give you for how heavy it is or for how much volume it takes. And so the general opinion was that this would be not a good idea because you add a lot of metal, so you decrease the energy density. But based on most probably similar models to what we are showing you here, Tesla has decided that this is worth it because at the system level, it provides you with much better benefit than the mass it adds. And then you can take these kind of models even further. And what we've done here is we are describing targets for what the average temperature and what the range of temperature across a pack or across a cell should be. And so you can look then with the model at the effect of choosing a particular cell and choosing a particular thermal management system, so a particular way to cool your battery. And you can make quantitative decisions about what is worth and what is not worth for you to put on the battery pack based on such models. So based on what Greg has said in the first hour, and also the little bits I've added, basically it would mean that we have the holy grail, right? We have the battery model that will solve our problems, and we can do so many things that are relevant to the industry with it. Unfortunately, it's not so. So there's still lots of scope for you and for us to advance the field. And there's sort of two different sources of problems with these type of models. The more fundamental one is here. So basically, a battery is not resistance and capacitors. It's just an analogy we're using, and it works within a limited space. But it's very difficult, if not impossible, to put inside such a simple resistors and capacitor model information about degradation and how different mechanisms of degradation couple. Information about how the microstructure or the porosity that you use in the separator or in the electrodes would affect the behavior. You basically have to build every single cell you can think of and then test it to get the parameters for such an ECN. You can't test what would happen without actually building the cell. You can't use it to optimize your space for the choice of materials. And you can definitely not test anything you haven't yet created. So for all of these reasons, ECNs are equivalent circuit networks are not the answer for all problems in terms of modeling. Plus, there is a whole field of people who are trying to improve how well equivalent circuit network models retrieve the behavior of even the known battery chemistries and designs. It just so happens, because the battery is not resistance and capacitors, that they are not very good at retrieving responses that contain many different characteristic times. So responses that happen both at a short time scale and long time scale. And so there is another type of modeling we use for this. I don't think Greg showed you this. This was just, I'm not gonna give you a lecture on degradation of batteries, but I just wanted to tell you that this is basically the most interesting and relevant current topic in batteries. How do we describe, understand, characterize, and predict not just one single degradation mode that occurs in batteries, but how they affect each other? Because you can think of a battery in a car, we'll see lots of different operation modes, right? Sometimes you charge it cold, sometimes you charge it fast, sometimes you charge it hot, sometimes you accelerate really quickly. So there's a variety of operational conditions, and each one of them triggers different mechanisms. And this image is not supposed to scare you. It's just supposed to say there's lots of different mechanisms that happen within the electrode pair of the battery, and they all happen within a very small space. And so it is to be expected that they affect each other. And sometimes it's a positive feedback, and sometimes it's a negative feedback between them. And so quite a lot is known about individual degradation mechanisms, but not much is known about how they affect each other, and how, you know, if you have one for the first few cycles, but then you have a different one, how those two will affect the battery performance. And so to study and to have a model to study this coupling, and to have a model that can predict how this coupling occurs for different batteries and for different uses of the battery, you cannot use an equivalent circuit network. You need a different type of model that is more based on the physical mechanisms that occur inside. And I put here another example. You know, these are just two of very many examples of when an equivalent circuit network model is not sufficient. So this is a group in Oxford who does gradient batteries. So they look at how they can create electrodes with different porosities to achieve better transport of ions, and thus better performance in the batteries. And again, you could not use an equivalent circuit network to retrieve the effect or predict the performance and sort of choose how to optimize your electrode microstructure for a particular application. I think you've briefly looked at this. I realize that your knowledge of batteries may be very uneven. Don't worry, you don't need to know much about batteries for what I'm going to say. Just to say that, you know, we're going now from the image of a cell, pouch or cylindrical, to the image of an electrode pair, because it's at this level that we are going to treat and try to retrieve these phenomena that I've talked about, such as microstructure effects and degradation effects. And what I was going to try now, let's see if that works, is to quickly draw how a battery works, because before deciding what mechanisms we would include inside battery model, we need to know which mechanisms are taken. Couple of minutes tutorial. Hopefully you see me having made a wonderful circle here in red on the slide. If not, please shout. About what happens when a battery, let's say, discharges. So we have here the negative electrode, and I just it's not a sphere. Yes, it's just some mass of porous material. We have a negative electrode and we have a positive electrode at this new length scale we are looking at, just between two current collectors with an electrode pair. And just for simplicity, I want one dimension, so that's why I'm doing a sphere. And the negative electrode is a material that was chosen because its energy state is such that when it's in this particular electrolyte, it wants to release, it's energetically favorable to release lithium atoms into lithium ions. And for this reaction to occur, sorry, this is a plus, it's also giving out an electron. Yeah, so this is in principle an electrochemical reaction happening between an ion and an electrode. And if you want to write it without the presence of the electrode, although it would not happen without, it looks like this. So this is a negative electrode in discharge. And if there is something there to collect electrons, and batteries will have materials put in that are good electronic conductors, this electron will be channeled to an outside circuit where, if everything else happens right, you can light a bulb, let's say, you can power something. Okay, at the same time, so this electron has flown through the outside circuit. At the same time, I have another material that was chosen because if its inclination in this electrolyte to capture ion, collect an electron for electron neutrality, and do what we are calling an intercalation relation, but it's an electrochemical reaction. Yeah, so on this other side, I have that lithium plus one electron coming through some conductive medium inside the electrode, goes to Li0 and inside the electrode. And so you can already see a few mechanisms that have to happen at the same time for this battery to discharge one electron, right? I need to have lithium 0 inside the negative electrode, and it needs to be at this interface, because it's at this interface only that the electrochemical reaction happens, which provides the electrons. I need to have lithium plus available at this other interface, and for this means over a long discharge that I need for lithium to diffuse inside the electrolyte. And I need here to have available location or interface for this reaction to happen in the reverse direction for lithium plus and one electron coming from the outside to provide a lithium 0 that is now inside the electrode. And there has to be space here, which means the lithium 0 has to be able to diffuse into the electrode. And finally, of course, I need to have all at the same time an electron conductor through the outside so the electrons can flow through the circuit. Okay, so it's going to be this sort of approach that we are taking to now build a model from bottom up by adding the equations that we think describe all of these phenomena. Okay, so we need to think about what the electrode potentials are, and I'm sure in the rest of the course you've already encountered these, maybe not for batteries, but for other electrochemical reactions. So we use the Gibbs free energy as a way to calculate the thermodynamic potential, gives us how much electrical work is available. And we get this Faraday constant, which basically tells us how we convert from moles of species, which is what reacts, to coulombs, which is what we're interested in a battery. And when we put it all together, we get this concentration corrected Nernst equation, which gives you the potential of an electrode in thermodynamic equilibrium. And you can do this for a lot of different materials. And I put here some of them that are of interest for battery electrochemistry. So based just on the thermodynamic potential obtained via the Nernst equation and obviously validated by experiments, you see here we can build a chart. So on the y-axis you have the potential, this thermodynamic potential of the different materials, and in orange are materials that are usually used for negative electrodes, and in blue are materials that are used for positive electrodes. And so as the gap between the two potentials is larger, so will be the voltage at the terminal of your cell, of your battery, and so the energy will be higher. So we're looking here for a large spacing between the negative and the positive material. And this is why carbon and graphites are chosen very often. Most of the batteries of the rechargeable batteries that you buy are based on graphite and carbon's negative electrode because they are very low, and so it allows you to have this large voltage gap between the negative and the positive. And then we can start, scoping for new materials in trying to enlarge this gap. And in fact, now the limit to why we can't separate them further is not that we don't have materials for the electrodes, but it is that we don't have electrolyte that is stable with respect to the electrodes for such high voltages, right? So we have high voltage cathode materials, but we don't have electrolytes that are stable there. The same here, you may see that I put here an SEI layer. This means that all of these materials, when chosen for negative electrode, lead to a degradation that occurs as a result of an undesired electrochemical reaction, and so on. So there's quite a lot you can do just based on the Nernst potential, but this is, of course, a very small part of the picture because we've assumed thermodynamic equilibrium. The next step to add is that as soon as I charge or discharge, so I use my battery, I'm outside thermodynamic equilibrium. I'm sending a non-zero current at that interface between the electrolyte and the electrode. And this comes with an activation barrier to drive a reaction outside of equilibrium. And I think you probably have seen this as well in other electrochemical systems. And the fact that here this barrier or this interface is in an electric field, so the electric field will have an effect on the cost of energy added to the voltage at the interface as a result of having this out of equilibrium reaction. When we put this together, what we get for the overpotential due to charge transfer reaction, so this electrochemical reaction driven outside of equilibrium, comes with a voltage penalty, and that is given by the Butler-Volmer expression. And the voltage penalty here is this eta. You can consider it as a delta V that comes as a penalty when the reaction is driven with a certain non-zero current. And this J is a mole current, but it can easily be changed via the Faraday constant into a Coulomb current. Okay, and so we have the thermodynamics, and that's that picture by which I choose my materials, and we have the kinetics, which gives me the cost of driving the reaction out of equilibrium, basically of charging and discharging the battery, and this is still not enough. So the voltage that you measure at the cell will be this OCV given by the two Nernst potentials, this Butler-Volmer cost of the charge transfer reaction, but I have other voltage losses. I have a voltage loss from the ohmic resistance, so this is everything that acts as a resistor inside the battery. It could be your tap connection, it could be your diffusion in the electrolyte, it could be your electron diffusion through the tortuous binders to reach the place of the interface where the reaction occurs, and so on. And I also have a very important component here due to the diffusion. So the fact that this is not bulk electrodes and bulk electrolyte, but it's a porous material. The reason why it's always porous is because we want to increase the interface in order to have more reactions. But because now we are having a sponge-like structure where the walls are the electrodes and is filled with electrolyte, all of the paths can be quite tortuous, both in the electrolyte, but also there is a limited diffusion inside the electrode. And so this is this diffusion over potential due to the concentration gradients you build inside the electrode and inside the electrolyte. So all of these act to decrease the voltage that you see in a cell. So here is a very quick diagram to see if you were to have this line as being your voltage for given by the Nernst potential. And now you look at what the actual voltage is at that electrode for increasing current density. You see how the penalties start building up. So you already have a lower voltage due to the charge transfer, you have a lower voltage due to any ohmic losses, and finally you have a lower voltage due to mass transport losses. And what is important to see in this picture is that all of these losses can have a significant contribution on your initial voltage. And they are dependent both on current and possibly on state of charge and definitely on temperature. So here with current, you see that at small currents, your activation, so your charge transfer, your Faradaic reaction losses are most important. But as you increase the current, and this is usually the regime where we operate batteries, your mass transport losses. So the fact that your lithium ions cannot transport quickly enough in the electrolyte, or the lithium atoms cannot transport quickly enough in this solid lattice that is the electrode, actually give a very significant contribution to the voltage of the cell. And so any model that is useful in determining how a battery performs as a result of internal design choices or external conditions will have to retrieve correctly all of these contributions to the voltage of the cell. And here I just put the same idea as before, but now we have the two electrodes, and we see that when we add the different overpotentials, our voltage hysteresis between charge and discharge of the battery increases. Okay, so let's start now to think about how we would build a model that takes into account all of these phenomena. And this is, I'm going to just introduce one class of models. They are called Doyle, Fuller, Newman, based on who has proposed them first, or pseudo two-dimensional models, and I'll show you why pseudo. So what sort of components and mechanisms are we aiming to include in our model? So we know we want some lithium ions in the electrolyte, and we have this Li0 charge neutral in the electrode, and they will appear, you'll see, as concentrations of species. We also have the electrons that we need to keep track of because that's what it's useful in terms of current. So this is what we can measure at the terminal. We can't measure the lithium plus in electrolyte in a real battery, but we can measure the electrons. We can measure the current and the voltage. And we will have the effective role of the electrodes through the Nernst potential. And then we want at least to retrieve these mechanisms: diffusion of both types of species, migration of any charged species, electrochemical reactions at that interface, and obviously conservation of mass, charge, and energy. We may also wish to include other features. Entropy plays a role in some electrodes that have significant phase change behavior. You've seen already from what Greg presented that very little useful work can be done without accounting for heat generation, and how all of these mechanisms depend then on the temperature of the cell. We may wish to start looking into degradation. Remember the picture with everything happening at the same time. And I just put here a few of the degradation mechanisms to just ring a bell that we need this kind of model to start seeing how these mechanisms may play a role in the performance of the cell. So particle swelling and cracking is something we may wish to look at, and this has been done in Billy Wu's group. Electrolyte drying is one of the very important mechanisms for sudden death of batteries. These are as a result of undesired parasitic reactions, which always happen at a higher or lower rate. We are definitely interested at some point to include lithium plating on the negative electrode, because now we know that this limits operation at low temperatures and especially charging. and we may wish to introduce this new different undesired electrochemical reaction that leads to the passivation layer that I showed you, that as soon as we use graphite or carbons, we have this as a degradation mechanism. Okay. And this is how it's done in the classical sort of P2D model. We obviously have to still make a lot of assumptions, but we are aiming to write the equations that retrieve those mechanisms, and those actors that I gave you, so lithium plus and Li0, will basically become our unknowns that we are solving for. So going away from the real microstructure of the cell, we want to have this domain that is the electrodes, and we want to at least be able to retrieve two phenomena. One, the fact that I may have a gradient across the electrolyte of species, and so I need to be able to retrieve behavior of electrode that is close to a current collector versus behavior of electrode that is close to the separator. And so this is why you see these rows of blobs rather than just one blob for the electrode like I drew a few slides back. The other effect that we want to be able to retrieve is that the diffusion of Li0 through the solid electrode is the slowest mechanism. And so I want to be able to actually capture it exactly so. And this is why I have here spheres, so that I allow Li0 to diffuse inside these spheres. I know that the electrode is not spherical. This is just the first zeroth order approximation, if you want. I'm just assuming that there is this extra dimension, radius r, through which things diffuse, because this is going to allow me to make the difference between an electrode that has lots of Li0 at the surface and so can deliver a lot of power because a lot of reactions can occur at the same time, and the electrode that doesn't have a lot of Li0 at the surface may still have them, but they are deep inside and they take a while to come to the surface. So I end up with these domains where I have a separator which is a sponge filled with electrolyte, and I have electrodes that are effectively sponges filled with electrolyte, but in the model, this series of spheres. And it's inside these spheres that I told you I'm interested in this diffusion, which is the slowest mechanism, and it's very important for power rate of batteries. So for the diffusion, I'm not doing anything surprising. I'm just taking Fick's law for diffusion and solving it in one dimension, the radius of the sphere. And so this is why I was choosing sphere, so that I can solve it in just one dimension. As you'll see, the model is complicated enough as it is. And it's going to be at the surface of this sphere that I'm going to allow the Butler-Volmer, those Faradaic reactions to happen in order for electrons to be transferred in and out of the circuit. So this is what the Butler-Volmer that I showed you before looks like for batteries after a few assumptions. But basically it's the same, it's the two exponentials. I've just made enough assumption to group them as a hyperbolic sign, and I have a complicated term here just to account for the fact that I may have different concentrations in the electrolyte of this species and different concentrations in the solid. So the concentrations of products and reactants should affect this cost coming from the equation being driven out of equilibrium. And then I look at the equations between the two current collectors, and you may be able here to identify some of the terms. So this concentration of electrolyte is the lithium ions in the electrolyte, and I'm just going to look at how this changes with time, and it will be a result of gradients. So this is diffusion, and it will be a result of electric fields. So that would be migration. And then these phi's are the potential. So I'm also solving for the potential at every point in the electrolyte. You can also have a double layer that's added that screen the electrodes, as obviously you are in an electrolyte. Lots of assumptions, don't worry about this. This is what you end up with, yes. So it's a very large system. and this is to be solved through a finite difference or finite volume method. And you end up with a system of equations called differential algebraic equation, because you have both partial derivatives and algebraic constraints. So this is from, conserving mass and charge and so on. This is computationally rather difficult to solve, and on top of it, it has Neumann boundary conditions. And so you may know that if you have a system where Neumann boundary conditions are and internal boundaries occur, that increases the computational cost. It also makes it a bit more unstable. It also depends on a lot of parameters, and a lot of parameters that are difficult to measure or even difficult to define. So just because maybe you can't see very well here, let's just go back through some of these slides. So this is a diffusion coefficient of lithium in the electrolyte. You may be able to measure this outside of a battery, but it will depend on temperature. So in principle, you should measure this at different temperatures. If we go back to the diffusion inside the electrode, again, you have a diffusion coefficient, which is now for the Li0 inside the electrode. So you should try to measure that. It will also depend on temperature, and more importantly, it actually depends on state of charge. It depends on how many lithium are already in the lattice, because that essentially changes the structure of the solid. And so the mobility of further lithium added depends on what the local structure is. These are just two of the parameters you would need to get. They are not all. You need to find here some equilibrium concentrations, and you need to find the reaction rate constants. And obviously you need to know the Nernst potentials for the two electrodes, and so on. So you do end up having tens of parameters and a system that is difficult to solve. So is it worth it? Sometimes yes. And I'm going to show you now two examples of when it is worth it. So this is to show that it's much more straightforward conceptually to tackle adding all of those degradation phenomena that we think happen in such a model. This particular diagram is for the addition of lithium plating, which hasn't yet been done in an equivalent circuit network, but has been done into this type of continuum model. And this is work that has been done in our group. So you can now look at what sort of chemical, electrochemical, and physical mechanisms retrieve the expected behavior for the lithium plating, one of the major degradation mechanisms that limits performance of real batteries in automotive. And you can start adding and coupling these equations to the system of equations that you had before. And Dr. O'Kane, Simon, in our group has implemented this both in COMSOL and in PyBAM. I just put here this because if you wanted to, you could play a little bit with such a battery model. So this is the model that I showed you, this continuum model that ends up with this differential algebraic equation system, and you can try it online. So there's not much. If you just want to use the model and run it in a few standard scenarios, just search for PyBAM. The code is also on GitHub, so you can also look to develop, and this is what we are doing. But you can also use it for free to try it out and see how it works. And this has been developed and is constantly being developed by our group and a few other groups around the country to constantly add new functionality and new science into the model. And you see this used already quite widely in the world. So this is definitely a story of success in terms of scientific computing and reaching to the entire community of battery modelers. Just wanted to say there's other available implementation. This is quite a standard model that a lot of groups are working to improve. And so if you're more into MATLAB, there's also this Lion Simba also on GitHub. This particular model that I showed you with thermal coupling that you can use. And also, if in your own research you already use COMSOL, you may already have the battery module. They also have a lot of implementations, both at the electrode pair level and at the full cell level. That, again, it's fairly easy to play with if you know COMSOL. And then another example of work that we have done quite a while back in the group, and I'm showing you this just because I think it brings it well then within the whole system picture. So here we were interested to optimize the number of layers within a cell of given thickness in order to achieve best performance for a particular automotive application. So this is the idea that we now have a cell of given volume, and we could fill it up with lots of thin electrodes and lots of current collectors, or we could fill it up with thicker electrodes and fewer current collectors. And it's already intuitive that the example on the left would give you a more power cell because you have lots of interfaces and you can draw a lot of current through all of the current collectors. You can also cool it better because the current collectors can serve well to eject heat from inside the cell. While on the right-hand side, you will get a battery that is more energy prone, so it has a higher capacity because more of the space in it is used for storing lithium, but that lithium is only available if you wait long enough, so cannot deliver high powers. It's a long range, but you always have to draw low currents from it in order to achieve that long range. And so this is again to see this balance, you know, that the few thick electrodes would give you good range, an energy dense battery, and lots of layers and current collectors inside the cell will give you a good rate capability and power. And so the two extremes are clear in terms of what we understand from the battery, but there is no, you know, rarely do you want a battery that has a very long range that you can never achieve because you would need to draw to low currents, or has very high powers but very short range. So how do you decide where in between these two extremes you want to be? And so this is the paper written now a few years ago, where we basically went from a powertrain to look at the request on the battery pack, to split the battery pack into cells, to end up to the level of what an electrode pair would see in terms of power requirement. And then we have used a thermally coupled model, like I've showed you before, the continuum model, but now with heat generation and with everything dependent on temperature. We have used that model to determine how many layers you need at least in order to achieve good performance for a few contradicting conditions. So we looked at the effect of the thermal management, and we wanted to be able to achieve a certain charging power while not degrading via lithium plating, and while not reaching temperatures of the cell above a certain critical temperature. So to have a maximum temperature that the cell can reach, after which you cut off performance, is quite normal. That's how you prevent spectacular and devastating failure. And so you want to have temperatures lower than that critical temperature, but also you want to not plate. And these are, in terms of what happens in the mechanisms, are contradicting. And so these tables are then generated from the perspective of the cell and tell us how many layers you would have to put inside your pouch cell to achieve all of these conditions for different types of automotive applications, for different types of ambient temperature, and for different types of thermal management. And so this shows you how we can now take this model that in principle looks at very zoomed in onto the electrodes, but correctly retrieves the physics going on, and pull it out into conclusions and optimization exercises that are useful for designing cells that would then go into packs that would then go into an electric powertrain. And now I just have some final remarks and was hoping to open the discussion if you have any comments or questions. So this is not a summary. This is just some thoughts to leave you with. So I told you that the current aim is to create this battery that can completely retrieve a model that can completely retrieve everything that goes on inside the battery. We call that a digital twin. And the idea is that once you would have that, you could use it for all sorts of optimization, whether you are a manufacturing engineer or a battery engineer, or whether you deal with warranties and predicting cycle life, whether you do with energy trading, with renewable sources, and so on. So this is what a lot of the community is currently working on. There isn't currently no ideal solution. We don't have a perfect model that can tick all the boxes. And usually the more comprehensive a model is, and the more physical it is, the more computationally and parametrizationally intensive it is. And so there is a lot of scope for new bright minds to come into the community and to solve a lot of the problems that exist. But I wanted to say that compared to where the field was 10 years ago, there's been such staggering amount of improvements, both in computational solvers, so they are much faster, and also in how we parameterize and characterize batteries to input that information into the models, that it seems now that a digital twin is not only possible but probable within the next 5 to 7 years. So it's definitely a good time to join the community and do some very impactful interdisciplinary research. So watch and join this space. Thank you.